3I Atlas isn't behaving like any comet or asteroid we've ever seen. It's not simply weird, it's impossible.
On a calm September night, astronomers watched as 3I Atlas, once thought to be just another interstellar comet, did something no natural object should ever do. It changed direction, deliberately. Then it pulsed at prime number intervals. Michio Kaku went on air and said it plainly, "Nature doesn't navigate."
If a comet were to hit the Earth, watch out. It would be a planet buster. It would be an object sufficient to wipe out all life as we know it on the planet.
Now Atlas is hovering just beyond Mars, in perfect balance, after executing maneuvers only spacecrafts perform. If this isn't a comet, what exactly is it? The turn that shook Kaku. In September 2020, 3 observatories, Mauna Kea in Hawaii, La Silla in Chile, and the South African Astronomical Observatory detected something strange. 3I Atlas, originally discovered in March 2024 and confirmed as interstellar due to its hyperbolic trajectory, was not behaving like any known comet. It had been following a predictable path through the solar system, just as expected for an object entering from deep space. But then, it changed direction. Not because of gravity, not because of random jets of gas. It moved in a clean, calculated shift mid-trajectory. The movement wasn't chaotic like most comet behavior. It was smooth, and then it repeated, once, then again, at precise intervals. Every 17 minutes, Atlas pulsed forward, a short, sharp burst of acceleration, not violent, not random, just enough to change its orientation and nudge it closer to the orbital plane of the planets. This wasn't just strange. It was surgical. Within hours, simulations began failing. Modeling teams from Harvard, Caltech, and the European Space Agency watched their predictions break apart. The data refused to stabilize. Each new motion made the previous trajectory obsolete. The object was adjusting, just like a spacecraft would. That was when Michio Kaku stepped in. He appeared on television with a calm, measured tone, but the words were unforgettable. "We should not expect flying saucers," he said. "We should expect the unexpected, a change in orbit, a sudden correction, a signal that something is obeying logic, not nature." And that's exactly what scientists were seeing. Atlas wasn't rolling or fragmenting like a comet approaching the sun. Its orientation stabilized, its spin slowed, and the timing of each burst was too perfect to ignore. Observers in Hawaii, Chile, and South Africa all confirmed the same thing. These were not outgassing events. They were deliberate thrusts. The intervals between them were mathematical, consistent. Orbital dynamics experts quickly recognized the maneuver. It was called orbital trimming. It's something spacecraft do when preparing for a gravity assist or a precise flyby, not something comets are supposed to know. More observatories scrambled to catch up. High-frequency tracking began. Thermal scans, light curve analyses, deep radar sweeps, anything to make sense of the pattern. And still, the object moved with intent. No random veering, no crumbling tail. Instead, Atlas was refining its path, zeroing in on a stable, predictable course, closer and closer to the planetary plane. For anyone studying orbital mechanics, the message was loud and clear. If this was a natural object, then our understanding of physics was broken. But if it wasn't, then 3I Atlas wasn't just passing through, it was driving. Prime number signals. A Chilean observatory team, analyzing James Webb infrared data, noticed something unprecedented. 3I Atlas's emissions weren't random, they pulsed, at perfect intervals, 131 seconds. Then 173. At first they thought it might be sensor error, maybe a calibration bug. But the same pattern appeared again and again. In readings from ground-based observatories, in logs from South African and Spanish astronomers using private infrared arrays. Even amateur setups picked up the same rhythm. Different tools, same pulse, room for error disappeared. SETI protocols are clear. A signal must meet 5 criteria before it can be considered non-random: narrow bandwidth, a source beyond Earth, repeatability, structure, and persistence. Atlas's emissions began ticking through that list one by one. The prime number pattern wasn't just a curiosity, it was a warning bell. Prime numbers, numbers that are only divisible by themselves and one, don't occur naturally in timed sequences. They lack rhythm. They don't show up in explosions or radiation decay or comet outgassing, which is exactly why they're used to flag intelligence.
Now, until recently, we haven't seen dust being pushed back behind the object by the solar radiation pressure.
They're intentional. In 1974, the Arecibo message used a prime sequence to introduce Earth's first radio transmission aimed at extraterrestrial listeners. It was the simplest way to say, someone made this. And now an object in our solar system was responding with the same idea. Michio Kaku spoke plainly. The moment a signal is built on prime intervals, he said, it is no longer in the world of rocks and gas. It is now in the world of logic. But could it still be natural? Some physicists argued that a comet's rotation might produce regular emissions, that if surface vents were spaced just right, they could release gas at fixed intervals. But that logic collapsed under closer study. Comets don't spin evenly. They wobble. Solar radiation melts their surfaces unevenly, creating chaotic, unpredictable jets. But Atlas didn't wobble. It didn't fragment. It stayed smooth, and the pulses stayed on time. Other theories pointed to solar interference, background noise from the sun creating sensor illusions, but that failed too. The pulses continued even after Atlas moved beyond the sun's interference zone. And worse, the pulses weren't radiating in every direction. They were directional. Leaked logs from a European observatory suggested that the infrared emissions were aligned along a single vector, not a wide beam, a narrow one. And that beam was roughly in the same corridor Earth would enter during its next orbital alignment. It wasn't pointing at Earth, but it wasn't avoiding us either. Around this time, several radio observatories began picking up faint microwave harmonics, barely detectable, but consistent with the infrared pulse timing. This wasn't strong enough to be called communication, but it was structured, a pattern, enough to keep going. Then it stopped. After 12 days of perfect rhythmic pulses, Atlas went quiet. That was when the military started paying attention. Satellites were repositioned, listening arrays recalibrated. Whatever Atlas had been sending out, it was over. And now, something else was about to begin.
We'll pick out objects that are moving inside of the four frames, and we have to identify if they are real or if they are false detections.
A movement that mirrors design. Over 17 days, Atlas executed what NASA engineers recognized immediately, a mathematically precise orbital insertion sequence. Each course correction was small, calculated, and perfectly timed. Not wild outgassing, not chaotic drift. These were adjustments, and they all bent the object's path closer to the ecliptic, the flat plane where the planets orbit. That kind of realignment isn't random, it's designed. In spaceflight, one of the first things NASA or ESA missions do after launch is shift their path to match the ecliptic. It allows for easier flybys, better imaging, and smoother gravitational assists. And now an object from another star system was doing exactly that. The corrections happened at exact points where orbital energy peaks. These are gravity sweet spots where small changes make a huge difference.
We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth.
Engineers know this principle well. It's called the Oberth effect. Fire a thruster at the lowest point of an orbit and you get more boost for less fuel. It's a real maneuver. NASA used it during the Voyager missions to slingshot past Jupiter and Saturn. Those tiny burns made it possible to reach the outer planets and beyond. 3I Atlas was doing the same thing. Each nudge happened where gravity gave the most return.
Soon, though, the comet's path will take it past even more of our robotic explorers.
And it wasn't just the motion, it was the precision. High-resolution imaging from the Very Large Telescope, VLT, in Chile, revealed something no one expected. Atlas wasn't spraying gas randomly like a typical comet. It was firing jets. Narrow, directional emissions, and those jets shifted orientation based on the sun's position. That's not passive venting, that's guided propulsion. Astronomers compared it to attitude control systems used on probes and satellites, systems that adjust thrust to change direction deliberately. Then things got even stranger. Orbital simulation teams ran Atlas's data through trajectory software. The result wasn't a curve or spiral or tumble. It was a clean sequence of steps, like checkpoints.
That new measurement then helps better predict the orbit fit next time someone needs to observe it to follow it up.
Each correction aligned it more precisely with the ecliptic. The math looked like a mission plan. If this were human-made, it would be a textbook insertion maneuver for passive observation. The timing, the intervals, the slow descent into perfect balance, It all matched what a satellite or probe would do to maximize visibility. The final move sealed the deal. After all the velocity changes and orbital burns, Atlas suddenly slowed. It dropped speed by almost 20% and settled into a holding pattern just beyond Mars, not skimming past, not crashing into the inner system, not breaking up. It held still. That's not what comets do, especially not ones from another star. They don't stop, they don't pause. Atlas did, and that's why scientists stopped calling it a comet, because it started behaving like a craft. Kaku's pattern alarm, echoes of Oumuamua. Oumuamua accelerated through our solar system in 2017 with no visible propulsion. 7 years later, 3I Atlas is repeating the pattern, but with added precision. Oumuamua's motion has puzzled scientists for years. It sped up while leaving no gas emissions or debris trail. No known natural explanation fit. Michio Kaku was among the first to suggest that it might not be a random rock, but something built, perhaps an ancient probe, long deactivated but still obeying its original programming. Now the same mystery is unfolding again. 3I Atlas, first tracked as a faint interstellar visitor, began showing identical traits: smooth course changes, acceleration bursts, and stable orientation. But this time the signals and timing are measurable in real time. Atlas is doing what Oumuamua did, but with visible structure. Over several observation windows, Atlas released a series of 17-minute bursts. Not 16, not 18, 17, repeated perfectly for 6 hours. Each burst increased its velocity by a fraction. Clean, precise, measurable. 3 separate observatories confirmed this: the Very Large Telescope in Chile, a Japanese infrared array, and an amateur setup in South Africa. All 3 saw the same pulse rhythm and synchronized increases in speed. This kind of coordination is not a coincidence. When analysts overlaid the data from Oumuamua and Atlas, the similarity was undeniable. Both objects showed acceleration near their closest approach to the Sun, exactly where the Oberth effect gives maximum efficiency. Both corrected direction toward the ecliptic after those bursts. Both behaved like probes, fine-tuning their trajectories. Statistical models put the odds of 2 unrelated interstellar objects doing this by chance at less than 1 in 5,000. For Kaku, that number was decisive. He had warned that if a second anomaly ever mirrored Oumuamua's behavior, we would have to consider a new possibility: that these were not accidents of nature, but examples of engineered design. The defense community noticed too. During Oumuamua's passage, internal reports later revealed that U.S. Space Command had independently tracked it apart from NASA. But this time, the response was immediate. The X-37B spaceplane, a classified orbital test vehicle, launched on a trajectory that matched Atlas's projected path. Officially, it was routine. Unofficially, it was too well timed to ignore. Soon after the launch, Atlas began producing smaller fragments. At first, they were written off as debris or ice breakage. But when their formation held steady, researchers grew uneasy. The fragments weren't drifting apart. They were maintaining positions, each at a fixed distance from the main body, moving together like a formation. High-resolution analysis revealed tiny fluctuations in spacing, consistent with autonomous stabilization. What spacecraft do when connected by telemetry. It looked less like disintegration and more like coordination. Some scientists compared it to satellite constellations like those used in modern communications networks. If so, Atlas wasn't alone. It was managing companions, tiny synchronized bodies possibly sharing one command system. Kaku theorized that if such formations exist, they could be part of an interstellar monitoring system, a kind of cosmic survey network. Not for invasion, not for contact, for observation. Quiet, systematic, mathematical. And if that's the case, then 3I Atlas isn't just a visitor following Oumuamua's path. It's the next phase of the same mission, now active, now aware, and far more advanced than anything we've ever seen pass through our skies. Not a visitor, a message. The observable data, course corrections, prime number pulses, formation-holding fragments, all point to one conclusion. 3I Atlas is not drifting. It's moving with intent. Every adjustment matches a maneuver from known spaceflight playbooks. Each thrust is timed with engineering precision. This isn't a wild rock reacting to heat or pressure. It's something different, something designed. And in this case, designed means engineered. The evidence suggests an autonomous probe following pre-programmed protocols. Not a crewed ship, not a signal-emitting beacon, but a machine. built to travel, to adjust, and to observe, across distances that most of our current technology could never cross. Michio Kaku never claimed this was proof of aliens. What he did say was just as important. He called it a design motion governed by engineering principles rather than physics alone, which demands we consider technological origin as a viable hypothesis. If this is a machine, it has instructions, it has intent. Even if that intent isn't directed at us, we're now in the blast radius of something artificial, something old, something far beyond our current understanding. So where does that leave us? Since October, global observatories have continued tracking Atlas's position beyond Mars. Agencies have redirected deep space telescopes to monitor for new pulses. Radio astronomy centers have been scanning for harmonics in overlapping bands. The X-37B, still in orbit, has reportedly made several trajectory changes toward the object's future position. No official statements have been released. At the same time, independent researchers and private networks are building open-source databases. They're comparing Atlas's timing patterns to known deep space signals, trying to match the motion to something in our archives. Searching for overlap. Atlas hasn't moved since settling into its holding pattern. And if this object is following a mission profile, we may be in the middle of it. Not at the beginning, not at the end, but right in the middle.